wish you could program something to move, like with the precision of clockwork, like a wheel, not just left to right, but by like specific rotations.
Okay.
Today we're diving deep into how a Java program tackles that exact problem.
What's fascinating is that the solution hinges on a seemingly simple tool,
Okay.
the for loop. It's like the engine driving our virtual wheel,
Yeah.
allowing us to repeat actions with incredible precision.
You sent me this intriguing program
Yes.
called Wheel Movement Problem.
Okay.
It takes user input, the wheel size,
Right.
how many moves it makes,
Yeah.
and how many rotations for each move. It's like a little interactive game.
Exactly. And that interactivity highlights the power of the for loop.
Okay.
It lets the program respond to each user command,
Right.
calculating and updating the wheel's position based on those inputs.
Okay, so let's break down how this for loop magic actually works.
Um,
I have to admit, those flowcharts from CEN 101W72425 were a lifesaver for me.
Yeah.
They visually lay out the loop steps.
Right.
Initialization, condition, execution, update, repeat.
It's like a recipe the program follows meticulously.
Okay.
First, we initialize, it's like setting our starting point, often with a counter variable like
Right.
Then comes the condition, the rule that determines how long the loop keeps running.
So in the wheel movement problem, the condition is tied to the number of moves the user chooses, right?
Yes.
Like if they say 5 moves, the loop runs 5 times.
Precisely. The loop keeps chugging along, processing each move until it hits that limit.
Right.
But here's a clever twist. The user can enter AO boom for the number of rotations,
Right.
triggering a break that stops the loop early. It's like a secret exit.
That's so cool. Gives the user ultimate control.
Yeah.
But before we get lost in the specifics of the program, let's talk about the update step in the for loop.
Okay.
This is where things get really interesting.
The update is crucial.
Yeah.
It modifies our counter after each cycle.
Okay.
Often it's an increment, like I plus A. Essentially taking a step forward with each rotation of our virtual wheel.
Right.
And here's the key.
Okay.
That invariable changes within the loop, making it incredibly powerful.
Now it's clicking. Alex Lee's video showed this perfectly. He used I to access elements within an array,
Yeah.
like picking out individual grades from a list.
Right.
Suddenly the loop isn't just repeating,
Yeah.
it's doing something different each time.
You've got it. Alex's examples highlight how versatile for loops can be.
Okay.
They can print the same thing over and over,
That's right.
but they can also interact with data,
Yeah.
changing their actions with each cycle.
It's like having a tiny robot arm,
Mhm.
picking out specific items from a conveyor belt based on your instructions.
Yeah.
So let's bring it all back to the wheel movement problem.
Okay.
We have the user setting the wheel's radius,
Mm-hmm.
choosing the number of moves,
Right.
and then dictating the rotations for each move.
And the for loop is the maestro,
Yeah.
orchestrating the whole process.
Right.
It takes those rotations, figures out how far the wheel should move based on its circumference,
Mhm.
and updates the wheel's position step by step.
Plus, it's giving us that interactive feedback,
Yeah.
showing us where the wheel ends up after each move.
Mm-hmm.
It's like watching a little progress report unfold.
Mm-hmm.
But before we get too carried away.
Let's take a closer look at the code itself, shall we?
Okay.
See how all these pieces come together to create this elegant simulation of wheel movement?
Lead the way. I'm ready to delve into the nuts and bolts of this program.
All right, so first, let's examine how the program gathers the initial information from the user.
Okay.
The program starts by prompting the user to enter the radius of the wheel.
So that's the first bit of user input. We're defining how big our virtual wheel is.
Right, and the program stores that value in a variable,
Okay.
so it can be used later on in the calculations.
Right.
Then it asks for the maximum number of moves.
That sets the limit for our for loop, right?
Yes,
Telling the program how many times to go through the whole rotation process.
precisely. And it stores that value in another variable called max hareket.
Okay.
You'll notice that the program uses descriptive variable names,
Right.
making the code easier to understand.
That's always helpful.
Yeah.
Okay, so we've set the stage.
Mm-hmm.
We have our wheel size and the number of moves.
Right.
What happens next?
Next, the program sets the initial position of the wheel to 0.
Yeah, okay.
This is our starting point,
Right.
like marking a spot on the ground where the wheel begins its journey.
Makes sense. You need a reference point to track the movement.
Yes.
Now, this is where the for loop kicks in, right?
Exactly. It starts with the initialization in I, A, 0. This creates our counter variable, I, and sets it to 0.
So I is like our move counter.
Yeah.
Keeping track of which move we're currently on.
You got it. Next comes the condition, I max hareket.
Right.
This means the loop will run as long as our move counter, E, is less than the maximum number of moves set by the user.
So the loop is directly controlled by the user's input.
Yes.
It's like a custom-made dance routine for our virtual wheel.
A very precise dance routine.
Yeah.
Now, within the loop, the program prompts the user for the number of rotations for that specific move.
Yeah.
This is where the interactive experience shines.
The user gets to decide whether the wheel spins left or right, and by how much, using positive or negative numbers.
Right.
It's like giving the wheel its own personality.
Exactly. And the program neatly stores this user input in a variable called character. Yeah. Remember that break we talked about earlier?
Yeah.
If the user enters 0, the program gracefully exits the loop, regardless of how many moves are left.
It's like a safety switch.
Yes.
Giving the user the power to stop the wheel at any time. So what happens if the user doesn't enter 0?
Then the real magic happens.
Okay.
The program calculates how much the wheel should move based on the number of rotations entered and the wheel's circumference.
Right.
It uses that classic formula, 2pi radius.
Circumference that takes me back to high school geometry. It's basically the distance around the wheel.
Precisely. And it's a key piece of the puzzle.
Yeah.
Because we need to know how far the wheel travels with each rotation.
Right.
The program multiplies the number of rotations entered by the user by the circumference to get the total distance moved for that particular move.
Okay, I'm visualizing it now.
Yeah.
The bigger the wheel or the more rotations, the greater the distance covered. It's like a virtual odometer.
Yeah.
Tracking the wheel's every move.
That's a great analogy. And once the distance is calculated, the program adds it to the current position of the wheel.
Okay.
Effectively updating its location.
So it's like keeping a running tally of where the wheel is on its path.
Right.
Each move builds upon the previous one.
Yeah.
Adding to the overall journey.
Exactly. And to keep the user informed, the program neatly prints out the wheel's current position after each move.
Okay.
It's like a little progress report,
right,
showing the results of each interaction.
So we see the loop cycling through each move, asking for rotations, calculating distances, updating the position, and reporting back to the user.
Yes.
It's a beautiful dance of code, all driven by the for loop.
And it highlights how for loops can break down complex tasks into manageable chunks, creating a clear and efficient flow of actions.
Okay.
But there's more to discover. Remember those other for loop examples from the CE 101 W7425 slides?
Yes.
The ones about perfect numbers and calculating supermarket points.
These seems like intriguing applications of the for loop.
Yeah.
Should we take a detour and explore those before we wrap up our wheel movement adventure?
Absolutely. They're great examples of how for loops can be used in different contexts beyond simple simulations.
Right.
Let's start with the perfect numbers.
Okay.
Those always fascinate me.
Okay, so remind me.
Yeah.
What exactly is a perfect number again?
A perfect number is a positive integer that equals the sum of its proper divisors.
Right.
Those numbers that divide evenly into it.
Okay.
Excluding the number itself. For instance, 6 is a perfect number.
Right.
Because its proper divisors. 1, 2, and 3 add up to 6.
Right. It was like a numerical puzzle.
Yes.
How would a for loop help us figure out if a number is perfect?
Imagine you want to test if a number, let's say 28 is perfect.
Right.
You'd use a for loop to iterate through all the numbers from 1 to 27.
Okay.
Checking if each one divides evenly into 28.
So the for loop is acting like a systematic checker.
Exactly.
Going through each potential divisor one by one.
And within the loop, you'd keep a running total of the divisors. If a number divides evenly into 28, you add it to the total.
So if we find that 1, 2, 4, 7, and 14 are the divisors of 28, we'd add them all up.
And if that sum 28 equals our original number, we know we found a perfect number.
Okay.
The for loop makes this process incredibly efficient, allowing us to test large numbers quickly.
It's like having a super-powered calculator that not only crunches numbers, but also follows a set of rules to determine a specific outcome.
You've got it.
Right.
And the same logic can be applied to other problems that involve checking a range of values and performing calculations based on specific conditions.
Like that supermarket points example.
Exactly.
It involved different points being awarded based on the price of each item.
Imagine a loyalty program where items under 20 TL earn 5 points. Those between 20 and 50 TL earn 10 points.
Right.
And items over 50 TL earn 15 points.
Okay.
Additionally, there's a bonus, 50 points, if the total spending exceeds 200 TL. A for loop could easily handle this.
So the loop would go through each item in the shopping cart.
Precise.
Checking its price and adding the appropriate points to a running total.
It would act like a digital cashier.
Right.
Tallying up the points as it scans each item.
Okay.
And after processing all the items, it would check if the total spending qualifies for the bonus points.
So the loop is doing more than just simple repetition.
Exactly.
It's making decisions based on the data it encounters and adjusting the calculations accordingly.
That's what makes for loops so powerful.
Okay.
They provide structure and control,
Right.
but they also allow for flexibility and decision-making within the loop.
It's like having a tiny programmable robot that can follow instructions,
I like that analogy.
make calculations, and even adapt to changing conditions.
And it highlights the core concept behind for loops.
Okay.
They empower us to automate tasks, process data, and create dynamic interactions within our programs.
So even though for loops might seem simple on the surface,
Absolutely.
they're actually the workhorses behind countless applications and systems.
And they're a fundamental building block for anyone learning to code.
Right.
Once you grasp the logic of the for loop, you can apply it to a wide range of programming challenges.
That's like mastering a basic move in martial arts.
I love that.
Once you have it down, you can use it in countless combinations and techniques.
It's all about building a strong foundation
Right.
and then using those foundational skills to create more complex and interesting solutions.
Speaking of building upon those skills,
Yeah.
those nested for loops we touched on earlier, those seem like a whole other level of complexity.
They are, but they build directly upon the principles we've already discussed.
Okay.
Remember, nested for loops are essentially loops within loops,
Right.
allowing us to work with data in multiple dimensions.
Like that example from Alex Lee's video,
Precisely.
where he used nested loops to create a grid of different colors.
Or think about creating a multiplication table. One loop could iterate through the numbers for the rows, and a nested loop could iterate through the numbers for the columns,
Right.
calculating the product for each cell in the table.
Okay. I'm starting to grasp how that would work.
You've got it.
It's like having two sets of instructions working in perfect harmony.
And this concept of nesting loops opens up even more possibilities for
Right.
creating patterns, processing complex data structures,
Okay.
and building more sophisticated programs.
It's like taking those building blocks we've been talking about
Exactly.
and using them to construct entire cities.
And the more you experiment with for loops,
Right.
both single and nested, the more you'll discover their incredible versatility and power.
Yeah.
You'll start to see them everywhere in games, simulations,
Right.
data analysis tools, and countless other applications.
It's like learning a secret language.
And what's even more exciting
Yeah.
is that there's always more to learn and explore. We've just scratched the surface of what for loops can do.
Right.
Who knows, maybe you, our listener,
Yeah.
will be the one to discover a groundbreaking new application for this fundamental programming concept.
Now, wouldn't that be something? So to our listener out there,
Yes.
we encourage you to keep experimenting, keep pushing the boundaries,
Yeah.
and keep exploring the endless possibilities of coding.
Remember, even seemingly simple concepts like the for loop
Right.
can unlock incredible power and creativity when used with ingenuity and imagination.
Absolutely. And on that note, we'll wrap up this deep dive
Okay.
into the fascinating world of Java's for loop. We hope you've gained a new appreciation for this fundamental programming tool
Yeah.
and are inspired to put your knowledge into practice. Until next time, happy coding.